as time-like. So if this is a time-like vector field, then it will have certain constant over it. But in 4D, for a congruence of time-like geodesics, you can actually write down your space-time piece into two parts, right? And it's transverse and longitudinal part. You can see the transverse metric H alpha beta can be written as the combination of G alpha beta and the U alpha U beta with this constant U alpha is -1. This is nothing but because of the time-like constant over there. And you can actually decompose your this evolution tensor in three parts. You can see the first part 1/3 theta H alpha beta. This is your trace part. This sigma alpha beta, you can just see this is symmetric and trace-free part. And last one, this omega alpha beta, is antisymmetric part. So this equation with this this decomposition of the B alpha beta, which encodes theta, sigma alpha beta, omega alpha beta, and the equation for B alpha beta dot, the first order differential equation for the evolution of B alpha beta, it actually gives the three equations which you can see over there. First equation here is for the expansion scalar. Second equation here is for the sphere, and third one is actually for the rotation. And you can see they are the first order differential equations. They are coupled to each other. They are non-linear as well as inhomogeneous. And this set of equation is actually true for any four-dimensional space-time background. Only thing, the things will get changed when you fix geometry. Whenever you will fix the geometry, and you can actually find the true meaning of these geometric parts over there. This, like in first equation, R alpha beta, U alpha U beta, this Chaudhary scalar, you can just calculate this by using the Einstein equations in GR. Even if not, if you have the space-time given to you, you can easily calculate that. And then you can try to solve these equations to understand the kinematics of geodesic flows and evolution in a given space-time background. So for the time being, as I already mentioned you, that I will be trying to solve these equations for Kerr black hole space-time background, and the space-time geometry for the Kerr black hole space-time is given by this line element. You can see this, and you can immediately notice that in addition to the coordinates, there are two parameters, J and M. J is actually for the rotation, and M is the mass parameter. But their ratio A is actually Kerr spin parameter. And once this spin parameter is not there, this Kerr black hole space-time geometry goes back to the Fauci black hole space-time geometry. And this space-time geometry is Ricci flat. Actually, in this case, this R alpha beta is 0. So we say this Ricci tensor piece has gone, so it's a Ricci flat. And by using this geometry, these equations now reduced in this form. You can see again, there are the three equations for these kinematical quantities, and you can immediately notice in the first equation this piece has gone, this R alpha beta, U alpha U beta. But in the second part, there is still wild tensor sitting over there, and they are actually coupled equations. So whatever geometric influence is because of the Kerr black hole, the curvature is still there, and it is actually coming out through this wild tensor piece over there. See, in the second equation, you can notice C alpha, beta, and beta delta, this piece over there, right? And it's really very difficult to solve these equations analytically. Very difficult. It's very hard to do that. In some cases, and in flat space background, we have analytically solved these equations, but in four-dimensional setup, we don't have still any clue how to solve them analytically. exact solutions. So in the absence of analytical solutions, what we do is that we try to solve these equations numerically by using some codes in softwares, right, like Mathematica and Maple, Mathematica, MATLAB, and then try to analyze what actually happens, how these kinematical quantities evolves, and what how they get changed with the parameters of the given space time. So in this particular case, we have given a new definition to theta, and with this redefining of theta, we have a Riccati type of equation there. You can see f double dot plus hf is equal to beta, and we can construct it as an equatorial plane of freely falling frame, and the components of shear and omega you can notice over there. Then with these, and by solving these, we have noticed few interesting things over there, and I can actually mention to you that what these interesting points are. When this h is greater than 0, this piece sitting over there, h, you can see again this equation, f double dot plus hf. Many of you have seen this, right? This equation is quite popular. You can think about a harmonic oscillator kind of situation there. Then if h is greater than 0, then there are conjugate points exist, and focusing and defocusing can take place. But if h is equal to 0, there is no finite time singularity for initially non-contracting congruences. Fine. And these are really technical ones. If you have not gone through GR steps, it might be a bit difficult, but still I will try to explain this. But one interesting thing what we have actually learned from our analysis is that even if the change is initial shear and rotation, there is change in the critical value of the initial expansion scalar. And the features of this focusing, defocusing remains qualitatively same for extreme and non-extreme Kerr cases. And you can actually visualize what I mean by focusing and defocusing. You can see this theta with this affine parameter lambda, there is a defocusing, right? You can see there's going, this theta is going, defocusing means this is going as plus infinity. You can see in this figures, and we have checked the role of initial rotation, and in one case we have taken no initial rotation, in other case we have taken some initial rotation. You can just notice omega 0 is equal to 0.1. So the escape of matter and energy from the black hole neighborhood, you can understand in that way what I mean by the defocusing, right? And the effect of the spin parameter A and initial rotation on defocusing is clearly noticeable in these plots. And in these plots, both initial rotation and A, you can see is actually going to advance the time to singularity, I mean defocusing here. And in the next plot, I will show you the focusing of theta, I mean when theta is going to minus infinity with the affine parameter, and focusing with some critical initial expansion scalar is clearly shown over there. And one interesting thing one can notice that initial rotation delays the focusing, while with A, the spin, the Kerr spin parameter, it has certainly opposite trend. You can notice it if you have, if you understand this what I'm saying, right? And let me try to summarize the results and the future possibilities in the direction. The angular momentum parameter A, which is J by M, it actually assists both the focusing and defocusing in Kerr black hole case. Larger the spin, earlier the focusing or defocus. In contrast with the role of A, an increase in the initial rotation always assists defocusing, and it delays the focusing in both the cases. So a very general result for applicable to any situation, any space-time background, we believe that the rotation always defies the convergence and shear always try to assist it, right? And the future possibilities, one can possibly study the accretion of matter into a rotating black hole space-time by using these equations. We are now in this, and we are trying to do some investigations that is this possible to study the accretion of matter into a rotating black hole, which is a very hot topic of research these days, by using the Rai-Chaudhary equations. And next is that we can also try to understand the kinematics of null geodesic flows. I mean, the photon, the motion of photons in these space, in the background of these space black hole space times. In this case, we have taken the time-like geodesic, and we have taken the real test particles. But we can also certainly study the null geodesic flows by using these beautiful equations. This is all what I was supposed to say in this talk, and I hope you could have understood few things, few new definitions, and I think I should stop now. And if there are any questions, I welcome you all. Thank you very much.
Any question? Any question? Nimai sir, any comment on the talk?
No comment. Very good talk. Very good. Very clear talk.
Thank you, sir. Thank you very much. Thanks a lot.
Thank you, Hemanti Nandan Pandey sir, for your beautiful talk. And you have explained the importance of Rai-Chaudhary equations in diverse contexts.
Yeah.
And its mathematical treatment.
Yeah.
And what are the future possibilities of these Rai-Chaudhary equations? Okay. You have explained very well.
Yeah.
Thank you very much, sir, for your beautiful.
Okay. Thanks for
thank you, sir. Thank you.
Thank you. Thanks to all of you.
Thank you, sir. Thank you. Now it is the time for lunch break. At 2:30 p.m. we will start next session at 2:30 p.m. Thank you, and enjoy your lunch at your home. Stay home. Stay safe. Thank you. Thank you.
One more information, please, for the participants. Please join your respective group, which are allotted for their presentation. Don't join other groups, otherwise you will not be allowed to present your paper in other groups. So you should keep in your mind that you should join in a right group at right time. So we will start the next oral presentation session at 2:30 p.m. Thanks a lot to all of you. Thank you, Nimai sir. Especially you are here this morning and continuously you are supporting us. Thanks a lot for that.
Yes.
Sir,
thank you very much.
Sir, you should also present at early in the morning tomorrow at 10 a.m. You are invited.
Yes, I will try. I will try. I will try.
Okay.